Welcome back everyone to AP Physics C E&M. Today we're going to be discussing magnetism and specifically electromagnetism and how the two relate to one another. So first we need to cover what is a magnetic field. Let's look at a simple bar magnet. Okay, North Pole, South Pole. The magnetic field extends outward from the magnet like this. Okay, in all directions. It makes a loop of sorts, okay? And the direction of the magnetic field is important. The direction always flows from north to south. All of the magnetic field lines flow from north to south. So if I were staring down the barrel of the magnet, like I was looking at the bar magnet like this, and let's say this was my south pole, then all of the magnetic field vectors would be coming out of the page at me like this, and you would see all of the magnetic field vectors represented around the magnet as such. And of course they would come out and they would all converge back in through the magnet, where the X symbolizes that they continue on through as such, where inside the magnet, the vectors flow from south to north, but you will never need to deal with that. The magnetic force is a force that is dependent on the movement of charge. That's why magnetism and electricity are often considered together, because they are so interrelated. Let's take a look at the magnetic force, okay? On your equation sheet, you can take a look that the magnetic force is equal to QV cross B. And magnetic force is equal to Q. What does Q represent? Charge. It represents the amount of charge times the velocity of that charge crossed the cross product of that and B, capital B being the magnetic field. From here on out, I'll refer to the magnetic field as the B field, so don't get confused on that. It is important to note how a B field is shaped, okay? And to do that, we use the right-hand rule, okay? Let me say that again. The right-hand rule, okay? I have gotten too many questions wrong because I was using my left hand for the right-hand rule. Don't be like me. Please use your right hand when doing the right-hand rule. Anyway, so there are two instances of the right-hand rule, okay? The first instance we're going to cover here. The second instance we're going to cover when we return to the magnetic force equation that we were covering just a few moments ago, okay? This, when we were talking about the magnetic field through a wire, can be illustrated as such. If I have a wire and current is flowing in this direction, then the magnetic field will be created around the wire as such, in a loop. And the loop has a particular direction, as you can see demonstrated by the arrows I am drawing. The magnetic field lines curve in a loop around the wire through which current is flowing, okay? And here is the right-hand rule. If I take my right hand, I open it up, I should align my thumb in the direction of current, okay? That's the step one. I align my thumb to point in the direction that current is flowing, and then I curl my hand as such, okay? Therefore, the curvature of my hand points in the direction which the magnetic field points, okay? So, since my fingers are curving this way, the magnetic field curves this way, such that the direction of the vector is the direction which the tips of my fingers are pointing, as can be seen here. If I illustrate it in another dimension, if I have my electric current flowing into the page, then if I take my thumb and using the right-hand rule, I point it into the page like this, which way do my fingers curl? They curve like this, which means the magnetic field curves around like this. Because that is the direction in which my fingers are curling. Okay? that is how we determine magnetic field around a wire. And again, the intensity of the magnetic field decreases as we get further away from the wire. Okay, back to this equation. The magnetic force equals the charge Q times the velocity of that charge crossed with the magnetic field, the B field. Let's give ourselves an example to help illustrate this, okay? I can draw a system right here. And let's say in this system, I have a magnetic field that is going in a straight line out of the page. Means it's coming out of the page at me. So the magnetic field would be illustrated with these circle dots, as I have covered previously. Magnetic field lines are coming out of the page right now. What this tells us is that in order for us to have a magnetic force, we need to have some charged particle, and that charged particle must have a velocity, okay? Now, again, this is an equation that determines the magnetic force on a charged particle. This is not the equation that determines the magnetic force between two permanent magnets, all right? We're past that point right now. Let's say I have a charge Q. Let's say this is a charge of 1 microcoulomb. Okay, and I got a charge right here, that's 1 microcoulomb. Let's say it has a velocity to the right of 10 meters per second. So let's look at our reference table to determine the units of the B field, okay? Force is a unit of newtons, and the units are kilogram meters per second squared, equals charge, Q, which is units of coulombs, times units of velocity, meters per second, times units of the B field, okay? We have kilograms present on the left side and no kilograms present on the right, so the B field needs to have units of kilograms. Meters are present on both sides. We need to have another seconds in our denominator, and we need to cancel out the coulombs. So these are the units for our B field. Kilograms per coulomb per coulomb second. This unit, the kilogram per coulomb second, is the Tesla, denoted as a capital T. So the strength of a magnetic field is denoted in units of Tesla. Okay? So let's say my magnetic field here is, I don't know, 10 Tesla, which for context is enormous. Okay? Like, usually you're going to be dealing with numbers in the micro or the millitesla, but for the sake of simplifying our calculations, we're going to call it 10 Tesla. The force on our particle by the magnet, by the magnetic field, I should say, is 1 times 10 to the negative 6 times our velocity, v, 10 meters per second, times our magnetic field, B, which is another 10 Tesla. Okay, now I am moving in this direction. My magnetic field is in this direction. So these two, my velocity vector and my magnetic field vector, are perpendicular to one another. Therefore, my sine theta term simplifies to 1 because the two are perpendicular. Now I know the magnitude of my magnetic force, which in this case is 10 to the negative 4 newtons, but I don't know the direction. How am I supposed to know what direction the magnetic force is operating in? That is where we come into the second interpretation of the right-hand rule. The first one was used to determine the direction of the magnetic field through a wire. This is to determine the direction of the magnetic force on a moving charged particle. Okay? Let's take our right hand, okay, and we're going to open it flat like this, and it's going to stay flat, okay? I am going to put my thumb in the direction of current, like it was before. Hey, Meek, I don't see any current flowing here. This is just a charged particle with a velocity. Yeah, That's the definition of current. Charges moving. So my current is in this direction. Then I want to take my fingers and I want to point those in the direction of the B field, okay? So the B field is coming out of the page towards the camera. So I'm going to point my fingers towards the camera and make sure my thumb is still pointing in the direction of the current, okay? Therefore, the magnetic force vector is the direction in which my palm points. In this case, my palm is pointing directly downward. That is the direction of my magnetic force. Now recall how this is exactly what I was telling us when I covered the cross product. The cross product determines a vector that is perpendicular to the first two, okay? So if I'm crossing a B field with a velocity vector that are both perpendicular in this axis, then my resultant should be perpendicular to the first two, which is going to point down in this case, as we can see. So moving on from there, let's try and understand how two wires might act on each other, okay? First of all, I might have a wire like this, and that wire is, according to this equation, going to generate a magnetic field around it. And the magnetic field, according to the right-hand rule, is going to curve around like this. So it's going to come out of the page on the left side, and it's going to go into the page on the right side, as such. Okay? Right-hand rule. If I have another wire going like this, which has current flowing through it, its magnetic field will be doing the same. Okay? So, since the magnetic field extends eternally but diminishes with increasing distance, it means that at the position of the, I'm going to call this wire 1 and this is going to be wire 2, at the position of wire 2, the B field contributed from wire 1 will look like this, okay? To calculate that force, we need to first identify that the B field from wire 1 is pushing out of the page like this. The current from wire 2 is moving upwards like this. So I have my thumb in the direction of current, my fingers in the direction of the B field applied to wire 2, and therefore the force applied to wire 2 is going to be in this direction. So the force acting on wire 2 is pulling wire 2 to wire 1. Okay? Now, if I were to reverse the direction of current flow in wire 2, without changing anything else, I would do the right-hand rule again. Magnetic field from wire 1 is going this way. At this time, my thumb should point in the direction of current that way. If the two wires have current moving in opposite directions, they will be repelled. And there's how the magnetic fields of two wires act on each other. Now we can use Newton's third law. Each force creates an equal and opposite reaction. So if wire 1 repels wire 2, it means wire 2 repels wire 1. If wire 1 attracts wire 2, it means wire 2 attracts wire 1, and we don't need to go through the whole rigmarole of calculating the direction of force of 1 on 2, and then to calculate 2 on 1. So, from that, let's move on to a bit more of an abstract concept, magnetic flux, okay? The math is simple, the visualization is not so much. Magnetic flux, if we look at the equations on our equation sheet, represented by the capital Greek letter phi, equals the B field dotted with the A vector. Okay. Magnetic flux, well, what's magnetic flux? Magnetic flux is the amount of magnetic field lines that permeate a two-dimensional area. To simplify that, it's basically how much magnetic field comes through a defined space, okay? Means that if I increase the space, the amount of magnetic field that comes through that space should increase. If I increase the strength of the magnetic field, the amount of magnetic field that comes through a given space should increase, okay? And that's what this equation is trying to tell us. If I were to draw a representation, let's say that the given space I'm trying to analyze is this box, given it's a 2D area, because we are dealing with 2D area in the equation, with side length 4, let's assume it's a square, such that the area is 16, and the B field would be 12 microtesla. My magnetic field were to be coming directly out of the page as such, then my magnetic flux would be maximized, because remember that the dot product is the magnitude of our two vectors multiplied together, multiplied by the cosine of the angle theta between them. Wait, Meek, how do I get an area vector? That's weird. Area is just a surface. Yes, the area vector is the normal vector to a plane, okay? So if I were to draw the area vector to this square, the area vector would come directly out of the page like that, okay? If the square was laying flat on the table, the area vector would look like that. The area vector is the normal line to the plane, okay? I'd say that the magnetic flux is relatively high compared to further out, when the magnetic field lines become further spaced out, because as the magnetic field decreases, the density of the lines decrease. So if I were to take the magnetic flux through that area, my magnetic flux would decrease, because the strength of the magnetic field had decreased as I moved further away from the wire. Okay? Another common point at which they assess your knowledge of flux is when I have an area vector pointing directly up, and I have magnetic field vectors that are not parallel to the area vector. We note that the magnetic flux through the area decreases up until the area vector is exactly parallel to the magnetic field vector, in which our flux is 0, because as you can see, there are no lines cutting through the area, right? Which makes sense. If there are no lines cutting through the area, our flux should be 0. Electromotive force, epsilon, equals BLV. Okay? This equation describes the EMF induced when not a loop of wire, but a single straight line of wire moves through a B field. Let's draw the apparatus in which this is observed, okay? You would have two wires, and at the end of the two wires is a resistor, okay? On this side, the wires are open, and on this side there's a resistor between them, okay? Now, there is a B field coming out of the page throughout this area, okay? And I have a stick, a rod, a metal rod, a conducting rod on the two wires, okay? Consider them rails for right now, okay? If I were to slide this rod across the rails, that would induce an EMF in the rod, okay? So let's try and understand how this is working, okay? The equation tells me that the induced EMF in the rod, make that clear, the induced EMF in the rod is equal to the strength of the B field multiplied by the length of the rod multiplied by the velocity of the rod, okay? So if I have a B field of 10 Tesla, a length of 10 meters, and a velocity of 10 meters per second, that means my induced EMF is 1,000 volts. from this end of the wire to this end of the wire, I have 1000 volts. But that 1000 volts is going to flow through these conducting lines across the resistor to here. Okay? And that is a completed circuit. The magnetic field is forcing the charges in the rod to separate, and it's forcing them to go around this loop to complete the circuit. Okay? So let's again use the right-hand rule to look at this. I have a B field that is coming out of the page. Fingers go to the camera. Thumb in the direction of the velocity of my charges. So therefore, the force, the magnetic force acting on the charges is in the direction of my palm. The magnetic force acts in the positive direction for a positive charge. So a positive charge would be forced downward, but the magnetic force acts in the negative direction for a negative charge, which means positive charges are forced downward, negative charges are forced opposite my palm, upward. So this part of the rod will become positive, this part of the rod will become negative. So therefore current will flow this way around the apparatus. So one thing we should consider here is that since we're in the calculus course, the algebraic form of magnetic flux was, of course, the magnetic field dotted with the area vector. However, in calculus, we're going to be referencing it in the integral form, that the magnetic flux, phi, is going to equal the magnetic field at a given point dotted with the area differential through which that magnetic field is passing through. Okay? So this is going to be the exact same process, exact same equation as electric flux. But I know what you guys are thinking. You're all saying, oh no, there's magnetic flux now. We're going to need to deal with Gauss's law and Gaussian surfaces again. Well, I've got good news for you. Okay? There is no application of Gauss's law to magnetism because Gauss's law of magnetism states that the magnetic flux through a closed Gaussian surface being equal to the magnetic field vector dotted with the area vector is always zero. Okay? And let's understand why that is true, why this is Gauss's law for magnetic fields. Okay? Because if I were to draw a magnet, let's call it a bar magnet, where I have my magnetic fields, of course, going from north to south, making also a complete loop through the magnet. So, of course, the magnetic field lines flow like this, outward, circularly in all directions, okay? So if I were to try and draw a Gaussian surface, if I were to draw, like, let's say, a circle, or a sphere, rather, if I were to draw a Gaussian sphere through any point centered on my magnet, you would see that every magnetic field line that leaves also enters, okay? Therefore, all flux that escapes the Gaussian surface re-enters the Gaussian surface. Therefore, net flux is always zero, okay? That is in stark contrast to the electric field Gaussian surface, in which all electric field lines would always leave out in a straight line. Here, all magnetic field lines come out and return. And the way that works mathematically is here, we will notice that our magnetic field line is exactly parallel to our area normal vector. So our cross product would evaluate to 1 in this case. And here, our magnetic field vector is exactly anti-parallel to our area vector. So in this case, the dot product would evaluate to -1, and the two would cancel out. Okay? So that's a little geometric and mathematical proof of why Gauss's law for magnetic fields is always zero. Therefore, you'll never need to deal with this on your FRQs. It's just something you need to be aware of, okay? Another thing is we discussed that current carrying wires will be able to produce a magnetic field, okay? And we discussed how to use the right-hand rule, okay? If I have a wire in which direction is flowing to the left, I'm going to take my right hand, place my thumb in the direction of current, and when I curl my fingers, that's going to be the direction of the magnetic field produced by the wire, okay, as such. We have a differential equation on our reference table that describes the magnetic field intensity some distance away from the wire, okay? And that is probably the biggest equation you have on your reference table, if I had to guess. That is that the dB, the differential of the magnetic field vector, is equal to mu naught over 4 pi, which is a constant, mu naught over 4 pi, multiplied by the current through the wire, multiplied by the length of the wire differential crossed with the r hat vector, divided by the distance you are away from the wire squared, okay? Now this is a very complex equation to understand, so let's try and work through it ourselves right now, okay? So mu naught over 4 pi, that's a constant. That needs not be explained, it's just a constant we plug in. Let's discuss the rest of how this equation contributes, okay? So let's understand this equation in the context of a loop of wire, okay? Wherein, if I were to draw a loop of wire, and I were to consider the point at the center of that loop, I would have some wire, it would go in a loop like this, and then it would go back out, okay? So I want to find the magnetic field at the center of this loop of wire, okay? So every length differential, every small slice of this wire is going to contribute some magnetic field to the center, okay, because of the right-hand rule. Let's say, for example, that current is flowing in this direction. So I would wrap my hand around current and I would discover that the magnetic field is supposed to be pointed out of the page. Okay? So, first of all, in my equation is I, the current flowing through the wire. I don't think we need to explain that too much. We are going to be given the amount of current flowing through our wire and we just need to plug that in. Okay? Next is the length differential, dl. Okay? Since this is a differential equation, we're relating the magnetic field differential to the length differential. This is saying that the intensity of the slice of the magnetic field is related to the contribution from a small slice of the wire, okay? So each small slice of the wire contributes some magnetic field. So we're integrating over the length of the wire to sum up all of the contributions from all the little slices of the wire, okay? Now what's important to understand here is it is the length of the wire crossed with the r hat unit vector. Now recall that a unit vector has a magnitude of 1, okay? And the unit vector has only, therefore, a direction. So the r hat unit vector is the unit vector along the length of r. What is r? R is the distance between our point and the length, okay? So it's basically saying that if our length of wire is momentarily has a vector like this, and our radius vector momentarily has a vector like this, we are going to take the cross product of those two vectors. And we should remember that our cross products would simplify to the magnitude of the length differential times the magnitude of the r hat vector times the sine of the angle theta, okay? In this particular case, our angle theta is 90 degrees. Sine of 90 degrees is 1. So granted that this part of our equation simplifies to 1 in this particular case, and given that the magnitude of the r hat unit vector is always 1, we are left with this entire expression just simplifying to the magnitude of our length differential. So in this case, we're going to rewrite our differential equation is equal to our constant mu naught over 4 pi times I dl over r squared, okay? Now I have two different variables here. I'm integrating over r squared and length. So I'm going to want to do a change of variables. What is the length of a section of the circle? Well, the length of the entire circle is the circumference of the circle. The circumference of the circle is equal to 2 pi r. And if I want to differentiate the total circumference of the circle, if I want to differentiate the total length around the circle, I get the circumference differential, which what is a circumference differential? It's a length differential, because circumference is length, equals 2 pi the derivative of r dr. Therefore, this guy comes down here. This differential equals mu naught over 4 pi times I times 2 pi dr over r squared. Now I have r and r, my variables agree. First of all, I'm going to notice that these 2 pi's are going to cancel, and I'm going to rewrite this in integral form. The integral of the magnetic field differential is equal to mu naught over 2 multiplied by I over r squared dr. We're going to do the integral of that. We're going to get that the magnetic field at our point is equal to, we're going to pull all of our constants out, mu naught I over 2 times the integral of 1 over r squared dr, which is therefore going to give us the B field at the center of a loop is equal to mu naught times I over 2r, okay? Now, we got a negative in our integral, but the negative in this case would only serve to specify the direction of the B field, okay? So we don't want to specify the direction of the B field in our equation, therefore we're going to remove this and we're just going to say the magnitude of the B field at the center of the loop is equal to this equation, which is the equation given to you on your reference table, the B field at the center of a loop. Oh, I was wrong. It's not given to you on your reference table. So this would be a useful equation to know how to derive. Okay, I thought this was given to you. Apparently not. Okay, so we already know that the magnetic field can exert a magnetic force on charged particles, but what we need to extrapolate from that is that any current moving through a wire, current is a movement of charged particles. Therefore, a magnetic force will be exerted on any wire that is present in a magnetic field. So that is going to be an equation given to you on your reference table as the magnetic force, F sub B, that's E, F sub B is going to equal the current flowing through the wire times the length of the wire differential crossed with the B field. So the way that this integral is supposed to be interpreted is, let's say we have a B field that is going into the page in an area such as this one, and we have a current carrying wire flowing through it as such, then obviously at all points on the wire, the length vector of the wire is always going to be perpendicular to the B field. However, if instead I decided to switch this up and say that I have a B field going to the right of the page, represented by these arrows, and my wire is not a straight line but a circle, then the cross product between the length vector of my wire and my B field will be changing as we integrate across the wire, meaning that at this particular point the B field and the length of the wire are exactly perpendicular. However, in this point they're exactly parallel, okay? So you would need to rewrite this as the integral I times B sine theta dl, wherein you would need to get a function of theta as a function of the length vector. So in this case, if we wanted to find the magnetic force exerted on this circle, we would need to solve this integral, okay? So first, I want to take my sine theta and I want to express it in terms of the length of the wire. Well, first and foremost, I know that the total length of the wire is the circumference of the circle equals 2 pi r, okay? R d theta, if we want to switch around our differentials, which will function in this integral we have just derived. Therefore, I can pull this down here, and for this example, I can calculate the integral of I times the B field times R d theta sine theta, or R sine theta d theta. Now, I was just demonstrating this derivation so you would know how to find the magnetic force on this loop of wire. But because it is a loop of wire, the net magnetic force is going to be 0. It'll only induce a torque, but that's beyond us right now. But I showed you how to do this derivation, not so we could find the magnetic force. You can find the magnetic force just using common sense in this example, okay? If you don't see it right now, let's work through this with common sense together, okay? If I am pulling all of my constants out of the integral, the current flowing through my wire is a constant, B field's a constant, radius of my loop is a constant, I'm just going to be left with some constant c times sine theta, the integral of sine theta d theta. And I'm going to integrate from initial theta to final theta, 0 to 2 pi. Should know that this equals 0. But we can understand that geometrically, because since this is a closed loop, any force created by the magnetic field on this side of the wire is going to be exactly counteracted by the magnetic field acting on this side of the wire, because the current is flowing in opposite directions on either side. So any contribution from the right is exactly canceled on the left. All right. Let's move on from there to another equation you're given on your reference table, which is Ampere's law. Ampere's law states that the path integral of the B field dotted with a length vector is equal to mu naught times the current enclosed. This is more or less your Gauss's law analog for the magnetic unit, okay? So this operates rather differently, okay? If I were to perform an analysis on a current carrying wire in which current is flowing in this direction, as we already know, if we do the right-hand rule, our magnetic field is going to be wrapping around our conductor as such, okay? So basically what this integral is telling us is the length differential is referencing the length of the path taken by the magnetic field vector, okay? So you can see that the magnetic field vector forms a circle, so the length differential is a reference to the length of this circular path that the magnetic field is taking, okay? And it's saying that if I integrate the magnetic field strength dotted with the length differential, that's going to equal some constant multiplied by the current within the wire, or the current enclosed by the path, which in this case is just the current flowing through the wire, okay? So you'll notice that in any path that we trace out, the magnetic field is always going to be exactly parallel to the length vector at that point on the path, okay? So we can get rid of this dot product. And since at any point on the path, the magnitude of the B field is going to be exactly the same, this integral is just going to simplify to the magnetic field times the length of the path is equal to mu naught times the current enclosed. And since mu naught is a constant and the current flowing through our wire we can safely assume to be a constant, this states that the further away from the rod that you get, let me draw it here so we can understand. The further away from our wire that we get, the less intense our magnetic field becomes because the length of our path increases. So as the length of our path increases, the magnetic field strength must decrease to compensate and to keep the right side constant, okay? So let's return to that derivation that I had just concluded for us, that the B field times the length of the path equaled mu naught times the current enclosed by the wire, okay? So the length of the path, as we discussed, is a circle. So therefore our length is the circumference of our circle, 2 pi times the radius of our circle. So let's continue this derivation by saying that the B field produced by a wire is equal to mu naught times the current in the wire divided by 2 pi r, where your r is the distance you are from the wire. And so this is the much more useful form of the equation that we use to calculate the magnetic field produced by a wire at some distance r away from the wire. I don't believe this equation is provided to you on your reference table, okay, which is weird because it's a very useful equation to have, so you're going to need to know how to derive this. Okay. Moving on from there, we can use Ampere's law to derive the magnetic field within a solenoid. If you don't know what a solenoid is, I'll draw one for you like this. Okay? A solenoid is a electrical component where this is a long piece of wire. We have current flowing in this direction, let's say. And these are loops of wire. All right, if I were to do the right-hand rule, let's consider this particular section of the solenoid for just right now. I know that the current is flowing this way around the wire. Okay, if I consider just this section, that means the current is flowing downward in that instance. Okay, so if I take my right hand and I align it with the direction of current in that instance, I do my curling, I'd realize that the current, or rather the magnetic field induced by that current, is flowing to my right. Okay? Well, let me be more specific. It is flowing in this curvature around the wire. Therefore, if I'm looking at inside the curl, then the magnetic field would be flowing to my right. If I'm looking at outside the curl, then the magnetic field would be flowing to my left. Okay? Therefore, the contributions of all of these little lengths of wire around these turns are going to produce a magnetic field through the solenoid that is extremely powerful, because you are overlapping the magnetic fields produced by a very, very long piece of wire. If you take a very long piece of wire and you coil it up, then it becomes a much shorter piece of wire. But since the length of the wire stays constant, and we shorten the relative distance it travels, the magnetic field produced at the center is much, much, much more powerful. So if I then apply this derivation to my solenoid, I get that the magnetic field contribution from a single loop of wire is equal to the mu naught times the current flowing through that single loop divided by the length of that loop, okay? However, the magnetic field encompasses more current the more loops that it goes through, okay? So if I encounter 2 loops, if I traverse the same unit of conductor twice, then I enclose twice the current. That's why this is specified as current enclosed, not current through the wire. If I enclose 3 loops, I am enclosing 3 times the current. I'm enclosing the same current 3 separate times. Therefore, the B field in a solenoid is equal to mu naught times the current in the wire times the number of loops, big N. Okay? Now, on your reference table, this equation is given to you as the B field inside a solenoid equal to mu naught I times little n, where little n is equal to the number of loops per unit length, which is basically equal to n over L. So we now understand why this derivation works. So that is largely the material for this unit. We're going to introduce one concept now, which is technically part of this unit. If you have an exam on this unit, technically this concept will be on your exam, but it'll only be on your exam qualitatively. We are going to discuss this concept much more in depth, with much more math, much more quantitative analysis in the next unit. But this concept is that a changing B field creates an electric field, and that a changing electric field creates a B field. So an important thing to note here is that if I have a constant electric field, then I will not produce a magnetic field. It must be a changing electric field to produce a magnetic field. Therefore, and the same goes for the magnetic field. I must have a changing magnetic field to produce an electric field. A constant magnetic field won't work. So like if I were to put a wire here, there's no current flowing through that wire, so I shouldn't even draw an arrow. And I were to put a magnet next to it, okay? North pole, south pole. Magnetic field lines going to be flowing out like this, as we have discussed previously. If I just leave it like that, there's going to be no electric field created in the wire. because the magnetic field isn't changing. To change the magnetic field, I'm going to need to move this magnet, okay? I'm going to need to move this magnet such that the intersection of the magnetic field lines with the wire is changing. Only then do I produce a changing magnetic field, and only then will I induce an electric field within the wire. Okay? That's the qualitative aspect you need to know for this unit. Thanks, guys.